Hello. So today we'll be talking about GPIO, essentially the general purpose input and output. And we are still learning about BBB, BeagleBone Bone. It's pretty much a TI Cetera AM3358 processor. So essentially, when you think of GPIO, think of something that is able to output a high or low voltage, or it could read whether an external signal is also high or low, like reading uh, blinking an LED that's setting high or low, reading a button press that's reading if you press the button, triggering a relay in etc. So for this Beagle Blackbone, whenever you decide to work on a GPIO, obviously you will probably be working on, this, you'll be looking at this board, right? And typically all this header, this is where you have access to or interface with the GPIO. So obviously you would like to understand what port you could use for a GPIO, what configuration you could use. So since this is a um, you know system on chip, obviously, well, if you don't know, when it's system on chip, these pins could mean many things at one time. So it could mean only one thing at one time, but that one thing can change programmatically. So you could change it to um, let's see, you could change it to so many things, like I think I have it somewhere here, like a GPIO, like a UART, like a SPI. So you could change it to many peripherals based on your need. And how do we know which peripherals that is? So this is basically the data sheet of the Beagle Blackbone. And when we go here, we can see that this is the header pin. So this is pin expansion header pin 8 pin out. And let me go back to that picture. So this is pin 8, looking at the board. Top view, the right one is pin 8 and this is pin 9. So this is pin out for the pin 8. So whenever you start working on this board, you kind of want to see what you could do with the header pin. So if we're looking at header pin 8, you could see that in mode 0, all those pin values are this, it supports this. In mode 1, MMC, LCD, depending on the pin. But if you come over here, you can see mode 7 pretty much supports all the pins will become a GPIO when you set the system in mode 7. So that's, however, in this particular chip, we have up to 4 groups of GPIO, group 0, 1, 2, and 3. And each of those group is a 32-bit. I know it says 31, but 0 index from 0 to 31, but total is, oh yeah, right here. Total is 32 pins that you can connect and be able to use GPIO functionality. Then you have another 32 for group number 2, another 32 for group number 2, 3, etc. So when you say GPIO 1, that means this group number 1 underscore 28. That pretty much means that, so if you notice, this number goes from 0 all the way to 1 to 7. So that means that you have to 1 times 32 bits plus 28. That gives you pin 60. So this particular group, you will be, that represents pin 60 here. Just that's how you can use it in the Linux kernel. So let's talk about a little bit of pin muxing. So pin muxing is essentially this. So one pin being able to do multiple things, which is essentially from mode 0 to mode 7, total of 8 functions. So, and for our GPIO, mode 7 is typical. However, when you are setting your board into mode 7 or your pin into mode 7, there are a few things that you have to keep in mind. You have to set whether you want to read it or write it. So that's where this rxactive comes in handy. So how do we know this? This is the technical reference manual for this particular chip, and this is the configuration of the register with offset value. So this is the register field table, and you could see the lower bit is where you set the function of the muxer. So 7 is mode GPIO. Then in the 5th bit, this is where you set it to either receiving is disabled, that's you're setting 0. If you set 1, then receiving is enabled. So that means that you can read input and output value. All right, so we just went over this, and so in terms of being able to map the header, so being able to map this header to a particular name of the Linux kernel. So for example, P9_11, which is somewhere here. 11 will be somewhere. You have to, if you look at the board, you will be able to see it level. That's a little blur. But then that will be GPIO on the group 0. Then we'll come back to this because this is a little confusing. You know, the header pin label is, you have to figure out how to map it to what you will actually use in code in terms of referencing to either the address or the kernel naming convention. So we will come to this very soon. I will cover it. So so now how do we map this pin or GPIOs to the software? So that most likely, you know, when you are writing a C code, you will be accessing it through a dev mem, which is map function, essentially accessing the root file, aka literally like a virtual pointer to read and write to the dev mem map. And you could pretty much do that in C code, literally touching the address of the register, literally moving resistors. So it's actually pretty cool. So enough said, let's go ahead and get into our bagel board and try to see what this looks like. So for example, let's say that we want to look at our this is SSH. If you don't know what this is, check out my last video. I covered being able to SSH into the board on my Eclipse IDE, and this is the console, like serial converter console. So when I boot, you could see the output here as well. So I can possibly do it here as well, but I prefer to use SSH. So I can go ahead and list. So these are the app that I ran previously, and I can show the home Debian directory. So obviously, if you are giving if your goal is to, okay, I want to start using GPIO, I want to be able to talk to it, I want to be able to change the values, I want to be able to do some settings, you will like to map out or get some information about GPIO, how to actually reference to it on in code. So one thing that you can do is listing all the GPIO chips, and you could use this command. Now we're going into the kernel, debug, then we check out the GPIO. So this is quite useful in the sense that, let's make this a little bigger. So look at all the information that we were able to get from this. We were able to see from the first bank, which is GPIO chip 0, we have 32 GPIOs. The number 1 is currently assigned to an MMC drive, so it's claimed by this particular peripheral. 1 is also claimed, then 2 is also in the header actually. So this is pin 8_5, which will be here, somewhere here, and it's actually claimed right now, MMC1, so you can't really use it for GPIO operation. Now you could see that pin 8_12, which is probably going to be somewhere here, pin 12. I wish I can show my board and you could get the exact number for it, but I believe, let me check. So 46, 45, 46. So 1 is from here, so pin 8, P8. 1 is actually here, and this is 2, 3, 4, 5, 6, 7, 8. So this is pin number 8. And if we go back to P8_12, so we want to essentially, I think this was 8, 9, 10, 11, 12. So this pin right here, we can use it to, as a GPIO. So this is super important, when you want to see what is claimed by a GPIO and be able to interact with it. And pin GPIO 20, GPIO 22 is our user LED. 23, 24, 25. 24 is we should be 4 right here. So 21 to 24 is our user LED, and we can confirm that somewhere here. Let's say user LED right here. So we have user LED. I'm talking about the LED here. So we have 4 user LED that we can use to program. So let's search for user LED. All right here. So as you could say, even in the document, it documents that GPIO 1, 2, 2, 2, 21, 22, 23, 24. So if we go back to our map, 21, 22, 23, 24 is right here. And I see a conflict here. So this is GPIO chip 0. So basically the first group, and I'm showing that the user LED is all in group 0, and 21, 22, 23, 24. However, if I go to the document, only this is correct, but it's still 21, 22, 23, 24. I'll have to look into that. So, but I feel like I would trust what this board is telling me. because this is literally reading from the board, and the board is telling me what it can do. So I will trust this more.